How we doing? Getting into this chapter 10, trying to wrap it up here. Probably two more short lectures. So I also wanted to clarify a little bit more of what I was working on last time with this S and P mixing business, right? How the order of the 2 sigma g orbital switches with the 1 pi u. So I wanted to explain that a little bit better than what I did last time. So when we started this discussion, we were talking about how when we create, or when we start mixing rather, 2s and 2pz orbitals, that they make two separate sets, right? This set of when the 2s orbitals mix make the 1 sigma g and the 1 sigma u, and this set when the 2pz orbitals mix make the 2 sigma g and the 2 sigma u. And of course, when you use the 2px and 2py, that's where we start making pi bonds, which you can see I've got right here on my Mathematica simulation. And what's important to note with these pi bonds, right, they're off axis, right? You can see there's this node in the internuclear region. All the same, there is still going to be some overlap with this pi bond and with this, where'd it go here? With this 2 sigma bond, right? There is still going to be some overlapping regions there. And so what ends up happening when you get into, like nitrogen and oxygen, for example, which is filling up, because it's half filled or more, you've got electrons in all of those p orbitals, which will then contribute not only to the pi bonds, but also this 2 sigma bond, okay? And so this is what I mean with S and P mixing, which is driving this 2 sigma to get lower and lower in energy as more electrons are populated in it, okay? And it's because of the symmetry about the z-axis. So as we start populating more electrons in that range, you've got a more symmetrical distribution around the z-axis. And you can see that as a huge effect of lowering the 2 sigma g energy, whereas the 1 pi u energy remains relatively stable. Okay, so I just wanted to clear that up. So let's get into heteronuclear diatoms. Okay, and so this is going to give us the quantum mechanic description of a polar bond. So a polar bond consists of 2 electrons and bonding molecular orbitals of the form psi equals some contribution of atom A plus some contribution of atom B, right? So here our simple molecule is, the molecule AB, right? We're just doing this generic, okay? And so remember, these coefficients here in the front, these give us normalization constants. And in the case of a basis set, like what we have here, right, the linear combination of 2 wave functions, these coefficients really are like a weighting scale, okay? So they give us like the weight that each atom contributes to the polar bond, okay? So in a polar bond, these 2 coefficients are unequal, right? There's unequal sharing of the electron. So the proportion of the atomic orbital A in the bond, right, is proportional to that weighting coefficient, and that of B is related to its weighting coefficient, right? So that's kind of just what I was saying there. So a nonpolar bond, of course, then would mean the 2 coefficients are equal, right? They contribute equally. And also, interestingly, here an ionic bond, one of the coefficients is 0 and the other is 1. And if you think about which one of these has to be an cation or an anion, it makes good sense then that A here would be the cation and B would be the anion, because in this cation-anion system, the anion is in larger control of the electron. right? The cation has no electrons in its valence shell, or at least in its outermost shell, right? It's got, well, both have noble gas configuration, but the electron density is centered, we say, mostly on B, or entirely on B, okay? So, and the atomic orbital with the lower energy contributes the most to the bonding orbital, and the AO with the higher energy contributes the most to the antibonding orbital. So I'm just going to go through one example in full detail of this, and that's the classic, halogen, HF. We could also use HCl or HBr, but all of those molecules serve as really classic examples of how to start constructing a wave function of a heteronuclear diatom, and of course the description of a polar bond. So here we can see that right here, right? We've got the coefficients for hydrogen and the hydrogen 1s wave function, and the coefficients for fluorine and the fluorine 2p wave function, okay? And so as you might guess, this makes a sigma bond. So it's predominantly the F2PZ that's, I should really say FPZ, that's in charge, right? That's making the sigma bond. And so the way we start constructing not only these wave functions, but the MO diagrams is by first looking at the energy relative to its ionization limit, okay? So if we focus on just the hydrogen 1s, okay, this number, 13.6 eV, that actually comes from Rydberg's constant, right? So way back in the chapter 9, when we built up the hydrogen 1s wave function, and we described, this line right here would be the n equals 1 state, and right up here at the ionization limit, this would be in, equals infinity, right? So that's its full ionization limit, okay? And we could do the same thing for fluorine, right? Down here, this level, this would be describing the fluorine atomic orbital for not quite n equals 1, because this is the fluorine valence shell, right? So we'll say that for n equals 2. But then, of course, this is still the same reference situation as for the hydrogen, the ionization limit, okay? So fluorine requires a much larger ionization energy because it's more electronegative, right? As we remember from our Gen Chem days, okay? So this creates these first levels, which allows us to start to think about how to put together this solution, okay? And so now what we can see here, what ends up happening, so and I'm going to go through this in a little bit more detail next week, how we can start computing these energies. But effectively, what we're looking at here is the bound state for HF, okay? So down there would be the HF, that would be the 2 sigma G, okay? And then somewhere up here would be its anti-bonding orbital, okay, way up here. So that would be the HF 2 sigma U. And so we could then start to get at these coefficients by solving this wave function. So in other words, we would put this together as the Hamiltonian times psi HF is going to equal EHF, and then of course back to the original wave function. And so we would start making guesses at these parameters, not only to still satisfy the atomic energies, but also to solve for these coefficients. And so, and I'm going to describe that in a lot more detail in the coming weeks on a little bit of an intro into computational chemistry and how we can start solving things for complicated molecules. But effectively, what you can see, what ends up happening with this simple diatom, right? For the psi plus state, the hydrogen coefficient equals 0.24, and the fluorine coefficient equals 0.97. And so that's consistent with what we said Right here, the AO with the lower energy contributes the most to the bonding orbital. But now what ends up happening when you solve this basis set, right, for the psi plus minus, right? Because remember, when we, this is, really I should just say this is the psi plus state right here, right? To get that anti-bonding orbital, it would be, right, the psi minus state, right? Let's put that in so that we recognize that it's still connected to this generic example that I started by describing, psi A plus B, right? This is a perfect example of that. But you can see when these coefficients get, or when we solve the psi minus, the coefficients get switched, which is kind of cool. So now in the anti-bonding state, the hydrogen contributes the most, whereas the fluorine contributes the least. Okay, so actually I could say that's still positive 0.24. It's just minus the wave function, right? Okay, great. And so, like I said, there's a lot more complications into working out these energies and these coefficients. But what I want you to recognize for now, it starts by looking at the atomic energies and trying to solve for the energy by minimizing the energy of the bonding state. Okay, that's how this all starts, by minimizing the energy of the bonding state. Okay, moving on. So I want to get into molecular term symbols. And just like I said, if that wasn't clear, more on this in the coming weeks, a little bit of an intro into computational chemistry on complicated molecules. Okay, molecular term symbols. Let's do it. So this is going to be very similar to atomic term symbols. However, we're going to really rely on MO diagrams to get the correct term symbols, okay? And in this, I don't even really like to bother with the Clebsch-Gordon series here, because if we can use our MO diagrams, and including MO diagrams for the excited states, I think it's much more straightforward. Okay, so multiplicity, the 2s plus 1, that has its usual meaning. Instead of a capital L, like we use for atoms, we use a capital lambda for molecules, which is still representing our total orbital angular momentum quantum number. But now we have a new term right here, which is related to symmetry. And so this parity, right, that's all about the G or the U symmetry operation. So that turns out to be more important to notate in molecular term symbols. Okay. So lambda can take on values 0, plus or minus 1, plus or minus 2, etc. Okay, just like L. And the absolute value of lambda is what we're interested in. And so when that's a 0, it's a sigma. And that's analogous to when L is a 0 for atoms, it's an S. Okay, so there's that connection still there. When lambda is 1, it's a capital pi. And when lambda is 2, it's a capital delta. So how do we get these lambda values? All right, well, lambda is the sum of all of the little lambda values. All right, easy. And we ascribe, and we're only going to deal with sigma bonds and pi bonds. Okay, so a sigma bond has a lambda equal to 0, or really I should say a sigma electron. Let's be clear about that. These are electrons. Okay. And based on the number of electrons in those respective orbitals is how many lambdas that we will add up. All right. When we have pi electrons, lambda can be plus or minus 1. And it's arbitrary which one we pick as plus or minus 1. But what's important to note here is if we put something in the pi x, we'll call it plus 1. And if we put something in the pi y, we'll call it minus 1. I could switch these if I want to. It's arbitrary. But what's important is, however I decide I'm going to do it, if I call pi x plus 1, I have to call pi y minus 1. Okay, that's really important. And I'm going to go through several examples. Okay, so let's look at H2. And I'll remind you, H2, I'm not going to do the MO diagram because we remember, hopefully we remember, it's a very simple 1 sigma G2 is the molecular electron configuration of H2. And actually, let's just go ahead and, I can back it up. Right, here it is, my H2. So 2 electrons in the 1 sigma G, so it's a 1 sigma G2. Okay. So when I'm going to add up all of these little lambda values, I'm going to ascribe, so I have 2 electrons, right? So I need to come up with 2 little lambda values. And because they're both in sigma bonds, each one is going to be a 0. So that's a 0 plus a 0 to equal 0, which is a sigma. Okay, great. Well, what about nitrogen? Okay, so let's go ahead and quickly take a look through its MO diagram. Oh, here, I've got it right here. Okay, lovely. So in nitrogen, all right, I'm predominantly interested in the valence shell. So remember here, my 1 sigma U and 1 sigma G, that's making up my core electrons for this period, right? For this period, the 1 sigma G and 1 sigma U is the core. Once I start at the 1 pi U, 2 sigma G, etc., that creates the valence shell. So I'm going to add up all of these for the valence shell. And let's go ahead and note that nitrogen's valence shell is 1 pi U 4 2 sigma G2, right? So there's 4 electrons on the 1 pi U and 2 electrons in the 2 sigma G. But we have to remember, okay, the 1 pi U is technically broken up into 1 pi x U, and we could say there's 2 of them there, and 1 pi y U, and there's 2 of them there. So that's where we're going to see this plus minus 1 situation. Okay, I just want to check something really quickly. Okay, good. So now what we can see with nitrogen, so let's write that down. We know that it was 1 pi x U 2, 1 pi y U 2, and 2 sigma G 2. Okay? So now I'm going to do all 6 of these electrons for my lambda. And like I said, it doesn't matter if we pick plus 1 or minus 1 as long as we're consistent. So I'm going to pick plus 1 for the x. And that's going to go plus 1 because I've got 2 electrons in that pi xu. Well, now I've got 2 electrons in the 1 pi yu. So that's going to be a minus 1 and a minus 1. And then now I've got 2 electrons in the sigma. And sigmas get a 0. So that's a plus 0 and a plus 0. And lo and behold, that all equals 0. So N2 is also a sigma state. Okay. So let's see here. So what's coming next? Yes, let's keep moving on. Okay. And we'll keep moving on with these H2 and N2 examples. And I'll note that thus far we've come up with ground states that are both sigma terms. Okay. So, well, what about multiplicity? Well, the multiplicity means the same thing that it did before, right? It's, we know we've got doublet states, triplet states, and singlet states. Sorry, I'm just trying to find my place in my notes. Here we go. Okay, great. So for example, with H2, without even really going and adding up all of those electrons, right, we do it in the exact same way we did with atoms. What I hope you recognize is H2 has got 2 electrons, right, in the 1 sigma G2, and its ground state, they're paired up. That means it has to be a singlet state, okay? And similarly, nitrogen, if we recall, nitrogen, let's go back and just look at its MO diagram. Right, so nitrogen has everything all paired up as well. Like when we look at all of these electrons, it's a lot more complicated than H2, but they're all singlet states. They're all paired up. Okay, beautiful. So I'm not even going to bother doing the sum of all of the S values as long as I recognize what a singlet state is. Okay, and so let's go ahead and write that down. Remember that it was 1 pi x u2, 1 pi y u2, 2 sigma g2. Okay. So now what about our parity term? Okay. Well, a g times a g is a g. A u times a u is a g. And so we can kind of start to think of this as positive times positive equals positive. Negative times negative equals positive. And a u times a g equals a u. So negative times positive equals negative. So that's where these terms come from. Well, check it out. H2 has got 2 sigma g electrons. G times g is g. So that's a 1 sigma g. Beautiful. And then what about nitrogen? Well, nitrogen, technically it's got a u times a u here, which is a g, and a u times a u here, which is also a g, and a g times a g. So it's also a 1 sigma g. Okay? And so finally, there is one, so we're almost done with these term symbols, but not quite yet. So there's one more special symmetry term, and that's for sigma states only. Okay? And so the way this works for the sigma state, we have to consider that a sigma state can be created by this confluence of pi bonds, right? So when we're talking about something like H2, we have no symmetry things to worry about because it's entirely made up of s orbitals. So if I look at my sigma bond for H2, let's see here, I'm going to just draw the sigma bond, right? Which we know was created from 2 positive s orbitals. Well, if I go, so here is my internuclear axis, right? My symmetry operation that I'm going to go through is this, the center of inversion, right, that we talked about before. And when there's no change in that symmetry, so it's positive the whole way through, then we add an extra positive sign there. Okay? So our full molecular term symbol for H2 is 1 sigma g plus, and as it turns out, all closed shell homonuclear diatoms have this term symbol. Okay? So 1 sigma g plus, that is a good thing to recognize because that means all of our bonding orbitals are closed up. Well, as you might guess, nitrogen is also in that category. Okay? All of its bonding orbitals are occupied, right? The 1 sigma g, the 1 pi, and the 2 sigma g. Those are all filled up. So anytime we have that, we're always going to get a 1 sigma g plus. So how do we get that plus term then for nitrogen? Okay. Well, nitrogen is made up of, it's a sigma state, but it's a sigma state from the confluence of pi bonds. Okay. So now if we look at this symmetry operation here, okay, when we look at, I'm going to define this one as the pi x, and this one we'll define as the pi y. We notice that in this case, in this reference frame here, the pi x has this negative symmetry operation. It's changing signs. Okay? Whereas the pi y is this positive symmetry operation. It's not changing signs. Okay? So if we look at nitrogen and how we get to that, and remembering that we have a whole mess of this stuff, okay, we're going to have, the way this is going to work, when I break apart my 1 pi x u, both of those are negative, okay? So a negative times a negative makes a positive. Now what about the 1 pi y? Well, we define both of those as positive terms. And then, of course, the 2 sigma electrons are also both positive terms. So a negative times a negative gives me a positive, and there's positive symmetry operations the whole way through. So indeed, N2, 1 sigma g plus, is a closed shell homonuclear diatom. What about this O2 example? Let's go through this O2 example, and I'm going to go through this in full detail. And you can see what I've got here is a empty MO diagram. And I'm terrible at drawing these things by hand, but I think there's some real value into you either, making some of these electronically or drawing them out by hand and populating them up. I think there's some real value to going through and doing this, okay? So let's go through and do this full O2 example, all right? So we know that O2 has, I had to count for a second, 12 total electrons. But if we look at its valence shell, so 12 electrons, 6 and 6 from each, we're really only worried about, why did I just draw a blank there? Oh yes, because I'm looking at one diagram and I'm looking at this diagram. Apologies. Okay, so yes, 6 valence electrons, so 12 that we need to deal with. Okay, so let's populate them up. So we know that we've got 2 from each 2s oxygen, right? So that's going to go 1, 2, 3, 4. So we filled up that shell. So now I've got 8 left to distribute. So we'll go 1, 2, and then this is how we're going to fill this out. 3, 4, 5, 6, 7, 8. Okay, and you notice that I made a triplet state out of this because remember, one of Hund's rules, if 2 different degenerate orbitals exist, and that's what we have here with the 1 pi xg and the 1 pi yg. They're different, but degenerate. If 2 different degenerate orbitals exist, the lowest energy configuration is achieved with the triplet state. Okay, beautiful. So now, let's go and get the term symbols. And so as you might guess here, we know that this 1 sigma g and 1 pi u, it's all going to shake out to 0, right? Okay. Well, the 2 sigma g, that's going to be 0, okay? Well, remember, we did this example for nitrogen, and this is all going to work out to be 0, right? Because if I call the 1 pi x -1, I've got a -1 and a -1. But then on the other side, I've got a +1 and a +1. So that all cancels out to 0. So now the only thing I'm really going to consider is my 2 electron system right here, these 2 unpaired electrons. And this one gives me a -1 on this side, and this one gives me a +1 on this side. So -1 and +1 makes it a sigma state. Okay? I can also see that it's a triplet. Hopefully you recognize now that 2 upspin electrons like that is a triplet, so I'm automatically going to put 3 sigma. Okay? We can see that it's a G times a G to give me a G. And then also, what about my symmetry operation? Okay, well, I've got 1 electron in the X, which is a negative. I've got 1 electron in the Y, which is a positive. And a negative times a positive gives me a negative. So the O2 ground state molecular term symbol is the triplet sigma G minus. Okay, folks, it's been about 30 minutes, and what I want I'm going to describe one more term symbol, and then I'm going to stop because I'm going to go through loads of examples. O2, O2 excited state, N2, N2 excited state, N2 minus, N2 plus, F2, F2 excited state. So I want to go through all of these examples, and that's where I'm going to do that in a part B video. Okay, but one last term symbol operation to describe, and this is for when spin-orbit splitting must be taken into an account, which is going to be predominantly for doublet states. And what hopefully you recognize right now, doublet states are often free radicals, right? Because a doublet state is one unpaired electron, and it's a doublet because it can be up or down. Okay, so let's go through this NO example. I want to make sure I have it in front of me so I get it right. Okay, and so first I'm going to put together the full term. Okay, so if we walk through, here we can see that oxygen is more electronegative than nitrogen. And so I think I missed describing that on the heteronuclear diaterms, but one way we know which one is going to be lower is the more electronegative element is always lower in energy because it requires more ionization energy, right? Because remember, in this MO diagram, ionization is up here at the top. That's our reference frame, okay? So here we've got the NO electron configuration, and we can see that it is a radical, right? NO is one unpaired electron. So let's see. So we know that the two sigmas are going to wash out to be 0. We know that all of these bonding electrons are going to wash out to be 0, right? 0 plus 0, and -1 and -1, and +1 and +1. Those are all going to turn out to be 0. But now we've got one electron in the X. I can call that -1 or +1. It doesn't matter because of the absolute value. So that's my only lambda value, right? So that's going to be a pi state, okay? And hopefully I recognize that it's got to be a doublet because it's one unpaired electron. And so now we're not so concerned here with noting if it's G or U symmetry, because with doublet states, what's more important is to take into account its spin-orbit splitting. And so that is given by this omega, which is analogous to J for atoms, okay? And so omega is going to take on all values lambda plus S, all the way down to lambda minus S. I missed that. Or rather, because S can be plus or minus 1, right, what ends up happening is we're going to get two possible J values, just two possible, I can't talk, two possible omega values, just like we see two possible J values, right? There's the high J and the low J. We're going to have the high omega and the low omega, okay? And so here, if lambda is equal to 1, remember, we only want the positive value, then that means this omega for NO is going to be 3/2 or the doublet pi 1/2, okay? And so as it turns out that the doublet pi 1/2 is lower in energy for NO, so that creates its ground state. However, if we flipped the spin on that electron, that would make it the doublet pi 3/2 state, which would be an excited state. It would be slightly higher in energy, and it would be an excited state, okay? Which is kind of cool. All right, so now Like I said, in the next video, I'm going to walk through these examples, but I want to record that as a separate video because I've already been going for about 35 minutes. Okay, folks, so make sure that you follow me through these videos. And like I said, I would recommend, working with these empty MO diagrams, drawing them for yourselves, or, using these blank MO diagrams that I have right here. And you might even try going through all of these yourselves before watching my video, okay? All right, folks, happy term symboling.